Okay, so we analyzed this whole situation of a car parked on a slope and it's not moving. How about if it is moving, if it's actually sliding down a slope? Can you find the acceleration? Or can I repeat the whole problem from my first problem? Yeah, let's make that number 3, right? And repeat the problem, but this time with friction. So it's actually moving, and yeah, let me redraw this whole thing. And let's see, so let's repeat the whole problem of 100 meters and 30 degrees angle over here. And I have something, I want to slide down the slope, but this time I am going to have friction. So if you want to play toboggan, if you ever go skiing, that's another good example, go and find out what the friction of coefficient is. Maybe just toboggan for simplicity, right? If you don't know what that is, it's really fun. Go on Google, search out what that is, and you can find what's usually the toboggan sled made of. Usually made of plastic, right? So you have a plastic board, you're gonna sit over here, sit on that. So this is gonna make our plastic. So find out what's the coefficient of friction for plastic and ice, right? So that's a good one. In fact, it's not gonna be a static friction anymore, it's gonna be a kinetic friction, right? So what's gonna happen is you have a weight, you have a normal force that I should make it a little bit longer, but just want to keep it in the diagram. And you do have some friction like this, okay? So how long is this going to take for you to travel down the slope that is 100 meters tall of elevation at a 30-degree slope, all right? Another very physical thing, you can actually do an experiment. Once you calculate this, right, go to a mountain, estimate the slope. Next time it snows, a lot of you live in California, so it's just not 2-hour drive away from the closest snow mountain. And you can test this theory out and see if your number is actually accurate and makes the right predictions. All right, so let's see. Right, so what do we want? We essentially want the acceleration here. Notice I'm drawing a double arrow just to differentiate. That's not a force, right? So just to differentiate from my actual forces. Over here, I want to resolve, I want to write down Newton's second law, which we will, right? But because we have xy, we need to resolve any forces that does not lie on the xy axis. Right, step 1, draw the FBD. Step 2, right, resolve this, which I will draw some dotted lines so that I can have a Wx and Wy over here. Okay, what's going to contribute to my acceleration? Well, I'm going to point xy this way. So max, let's call it ax, yeah, is going to be Wx minus fk, right, the kinetic friction. And it's not accelerating in the y direction. So let's just obviously write down this has to cancel this, right? Otherwise, I will have a y acceleration. So if you want to justify that a little bit in your exam, you can write since ay equals 0. And this is a nice shorthand. The 3 dots means since. If you orientate that way, it's since. If you orient it this way, it's therefore. Okay, very handy, simple. Anyway, since ay is 0, you can directly claim that. Now, what we left to do is plug in the formulas. We've done that many times, so I'm just going to write that's 30 degrees. That's going to be 30 degrees. So Wy is the one that's going to sandwich the 30 degrees. So that's going to be cosine. That's going to be sine. So we're going to directly jump in here. W sine 30 degrees minus fk, which I know is mu kn. And here I know this is W cosine 30 degrees. And let's actually keep this as theta. The benefit of working with variables is if I change the question, right, suddenly I realize my slope is not 30 degrees, but it's 39 degrees. Now, if you don't work with numbers, you have to redo the whole problem again. So this is a benefit of analyzing a situation purely with theta. And if you see any physicists do the work, they try to keep everything as a variable until the very end and try to plug in things. And you have a better understanding of also how each things relate to each other, just like what we did with the tangent in example number 2 of incline plane number 2. The tangent we see a relationship between the variables more than just a number, right? So we get much deeper insights. What else we know, right? So there is, yeah, that's mg. There we go. And we see an n over here, and it's almost begging me to take this n, plug it in here, right? So you got to do whatever you've got to do. So you want to plug this in. So you have mg sine theta minus mu k. And so once you plug this in, you have mg cos theta. I have ma over here. What do I need to solve for time? Remember from the first video today, we talked about force creates acceleration, and acceleration tells me everything else through kinematics, right? So I really want acceleration. So my x disappeared halfway, so let me put that back in. We realize the m's cancel out, so we have the ax is g. Let me factor that out. Sine theta minus mu k cosine theta. All right, that is what we have, and that looks good to me. Why? Let's do some sanity checks, right? If I do not have any friction, so if I don't have any kinetic friction between my plastic and ice, it's going to be a pretty small number, I suspect. I haven't Googled that yet. Someone can let me know below what that number is, and plug in 30 degrees and see what the acceleration of that is. But if it's going to be 0, right? If there's no friction, what do I do? Well, I can easily just, I don't have to reanalyze everything. I can be clever about it. I can just set that to be 0, right? Then if the coefficient of kinetic friction is 0, then I have no kinetic friction. So if I set that to 0, I have g sine theta. Does that ring a bell? Yeah, I think so. If you look back at the first example, that's exactly what the acceleration is without any friction, right? So this seems promising immediately. Yeah, good. And what else? If I increase the slope over here, you can also see what happens, right? If I increase the slope, sine looks like this. Again, we're just interested in up to 90 degrees, not up to 360, right? So 90, 180, 270, 360. So 1/4 of the cycle. So sine is increasing as you increase the slope, which means you accelerate faster and faster. But cosine, if I divide this in 4 pieces, 1, 2, 3, 4, right, 90 degrees, it's a decreasing function in the first 90 degrees. Later on, it increases again, but I'm just worried about the first 90 degrees. So over here, this decreases. So if this decreases, that means, and also this increases, the whole thing makes it accelerate faster and faster. Does that also make sense? Yeah, it seems to make sense. Okay, what else can we say about this? Yeah, first of all, in terms of problem solving, which is something to actually get the answer of here, like I always say, that was the least of my concern, what that value is actually. You can Google what that value is, plug that in here, use the kinematics equation again, find out what T is, right? So that's the least interesting thing in some sense of this problem. But now you have all the tools to do it. One thing I want to address over here, one more, is usually we're given, right, G is a constant. That's something I cannot play with. The theta, let's say I have a standard theta, right? So these are all fixed. So what if I'm not going to use plastic and ice? I'm going to use something that this time it's not going to be ice anymore. It's just a grass slope. And I'm going to put something that's very, very frictionless. Is that a word? Let's make it a word. Very, very frictionless. So it's something with a very large coefficient of friction. So what's something very high coefficient of friction? I don't know. Velcro. Velcro on soil, on gravel, or even worse, on soil, let's say. So you have something that is extremely large coefficient of friction. Well, what's the maximum of sine? It's 1, right? Now, the maximum of cosine, again, is 1. But if I have something like 30, I don't know. What does that mean? First of all, can it be 30? Can it be a number larger than 1? Let's see, right? So the kinetic friction is equals to that. So that means this is telling me how many times is the friction force of the normal force, right? If this is 1, that means the friction force is the same as the normal force. If it is a very small friction, like plastic and ice maybe, right? Or metal and ice, this might be 0.1 or 0.01, something very small. So that means the friction is going to be just a small fraction of whatever the normal force it is between the surface of contact. Can it be 2 or 30? Yeah, absolutely. That just means that it is really, it's moving. If it's a kinetic friction, it's moving, but it's really, really high friction. It's just double the amount of normal force, and that's completely fine. You have Velcro, it can almost be infinite. Velcro on Velcro, and but yeah. So what happens over there? Well, whatever that number is multiplied by 30, this could turn out negative. What's going on here? Can A be negative? What do you think? Or you look at this and go like, yeah, I know what A is negative means. A negative just means it's not accelerating this way, it's accelerating that way. What's wrong with that picture? With a closer thought, if A is accelerating that way, that means, hey, if I put Velcro, like Velcro on Velcro on here, so I have a large kinetic friction, then my object is just going to spontaneously go uphill. What's wrong with that picture? That does not seem plausible, right? So what's going wrong here? It's because you're pushing the diagram beyond its domain of validity. So I've mentioned that a few times. So every now and then think about the domain of validity of your setup. So when you set up a problem, when you set up to solve a problem, there's always a domain of validity. That means what's the range, what's your region that your setup is valid. When is this valid? Well, it's valid as long as you're accelerating this way. What happens if you accelerate that way? Well, if you are accelerating that way, right? Or if you're moving that way, it's not even about acceleration, but it's about speed. If your velocity is moving that way, which way is the friction going to point? If you are moving that way, well, I can give you an example, right? You can have a box on the bottom, put it on a spring, it's going to launch it, and it's going to move, right? This is, again, not force, but it's velocity. It's moving this way, and in that case, the friction is going to act against you. So what you will have in this situation is the weight here that will work against you, a normal force that doesn't really affect your velocity, but there's a friction. So everything's going to try to, almost everything's going to try to slow you down. It is accelerating this way, but it's moving this way. So when it's moving this way, the friction is acting against you. So this is only valid up to a certain point. If this is actually going the other way, you should be drawing the friction pointing the other way. Otherwise, so this whole setup, even the first step, I am assuming that the box is moving this way. Remember, the friction is against its resisting motion. Okay, so keep that in mind a little bit, and someone who will figure out the time can also put that down below, and everyone can check if you understand this. If you can do this, you really has a good grasp of inclined planes.